All right. Hi, everybody. Thank you for coming to this talk. Um, this is part of a sequence that we're calling Introduction to Modern Mathematics, where various professors are going to give talks over the course of the next several weeks on different topics in math, many of which are sort of closely related to the kind of classes that you take in a sort of undergraduate curriculum in math, and also some graduate classes as well. So you should definitely stay tuned. We can give you a link to the Math Club sign up as well if you want to join and sort of get more regular updates for these kind of events. And yeah, thank you for coming. So today, Professor Hutchcroft is going to be talking about mathematical frontiers in phase transitions and critical phenomena.
Thank you. Thank you for being here. So, all right. So my first task is to explain the words in the title. Hopefully, mathematical is fine, and it's not so fine. Let's explain the other words. So let's start off by talking about phase transitions. So I want to keep quite a broad view and not very prescriptive view on exactly what this means. So sometimes in physics you'll see much more specific meanings of this, but for me, a phase transition means you have some kind of system which involves a large number of things that are interacting with each other. So you could imagine, you know, molecules in a gas or a liquid or something, or you can imagine, you know, agents in like an economic system, like a financial market or something like that, or you might imagine like cars in traffic, all these kind of things. They have a large number of components that are interacting with each other in some way, often with some spatial structure of the interaction, like you're interacting with things that are near you, and there's a large system, most things are far away. Okay, so in many of these systems, you have some parameters that describe the interaction, which can be very continuous. So things like the temperature or the pressure in a physical system, for example, or it could be like the density of cars on the road in your traffic model, something like that. And a phase transition means as you vary these parameters through some special value, if it's one parameter or maybe like a surface of values, you have more than one parameter, you get some kind of abrupt qualitative change in the behavior of the system. Okay, so of course, the example that you're probably most familiar with is like, melting and freezing, things like that, right? So as you change the temperature or the pressure in that example, right, actually, both of those parameters determine whether something will be solid or liquid or whatever. You get these change of phases where the behavior completely changes. Okay. Another example that you might not be familiar with in physics is in magnets. So if you have a piece of iron, right, as you know, if you expose it to a magnetic field and then take that field away, it will remain magnetized, right? Iron is ferromagnetic. That's actually not true for hot iron. So there's actually a phase transition at what's called the Curie temperature, which is well below the melting point of iron. So, eventually it'll become liquid. That's another transition. But there are two different states of solid iron where it is or is not a ferromagnet. Okay. And I was asked, by the way, to talk about like relevant courses at Caltech. There are a very large number of courses at Caltech where phase transitions come up, both in physics and in chemistry. Okay. But of course, as I was saying, there are many phase transitions outside of physics or outside of the natural sciences. So another example that I didn't mention yet is in like the spread of a disease, right? So if you have a disease that's spreading through a population, there's a parameter sometimes called R naught, so the average number of people that an infected person infects. When this is larger than 1, the disease will spread rapidly and take over the population. When it's smaller than 1, the disease will quickly die. Okay, but phase transitions occur all over the place. It's kind of in any sufficiently complex, like large system, you probably have some kind of phase transition, or maybe more than one. So they also occur a lot in theoretical. Okay. Now, what I'm mostly going to be talking about in this talk is what we call critical phenomena. So what this means is that many systems, when you tune them exactly to the point of phase transition, they exhibit very interesting, rich mathematical structure that is often reminiscent of like fractal geometry, so kind of fractal-like geometry. So, you might be thinking, well, I've seen water boil pretty often, and I've never seen a fractal appear. And indeed, that example, you don't really see this kind of thing, although you can get this kind of, at least in the mathematical structure, you can see this kind of rich phenomena in that kind of system, but not in the normal temperatures and pressures that you have in your house. But in many other cases, you do see this rich fractal-like geometry appear at the critical point. So this is a simulation of percolation, which I'll talk about much more, made by Jason Miller, and you can see you're getting all these interesting like curves that come back on themselves and stuff in a very detailed way. Okay. So one thing to mention straight away, one of the things that is most interesting mathematically about these kind of systems, although it's something that we very much can't prove, and maybe I should make that point more broadly before saying anything else. These kind of systems, they're a source of a lot of interesting mathematics, right? So, you know, I'm a mathematician. I'm going to be talking about this from that perspective. Of course, these are important, like, things to understand in the natural sciences, but they're very interesting mathematically, and they're generally very hard to prove things about mathematically. So I'll give you an example. It's an open problem in math to prove that water freezes when it's cold. Right? This is, nobody knows. Okay. Now, one of the interesting things about critical phenomena is that they're expected to exhibit a phenomenon of what's called universality. Okay, so this is actually really good for mathematicians. So the idea is basically that many of the fine details of how you define your model should not really matter when you're looking at the critical point. So these kind of details, they can change like the value at the critical point, which for engineering applications is extremely important, right? Like if you want to make a superconductor, it matters a lot how cold you need to make the material, right? Like if you can make one at room temperature or something, that's amazing. But if you're not worrying about the value of the critical parameter, but about what happens at the critical parameter, then like the difference between like different lattice structures or something like that in your model, they should not really matter. So, you know, if you do something, this is percolation, which I'm getting a bit ahead of myself, but if you do things with a square grid or a hexagonal grid or some, you know, continuous rotational symmetry, none of this should really matter. It shouldn't make important differences to what's going on at the critical point. And this is also related to another really interesting thing, which again, we can't really prove rigorously in many situations, which is emergent symmetry. So, you know, often I'm going to be telling you about models where we do something on a grid or something, and of course the grid will only have like 90-degree rotational symmetry, but what you expect is that at the critical point, this is not really a problem, and when you zoom out, you should get full rotational symmetry. But again, these things are hard to prove and not known in most cases. Okay, so you know the nice thing about this universality phenomenon for mathematicians or for physicists, for that matter, is you know there's this frequent criticism of physics, the spherical cow thing, right? Like, oh, you model a cow as being a sphere, and of course that's not a good model of a cow. But actually, in statistical mechanics, it doesn't really matter that much, actually. At least that's what we believe to be the case. So, you know, we can work with mathematical models that you might think seem to be very coarse approximations of what's really going on, but that actually shouldn't matter very much, at least if we want to understand what's going on at large scale. Okay. Now, on the other hand, one thing that is very important is the dimension. So a 2D system should behave very differently than a 3D system, very differently than a 4D system. Like this is really an important distinction, even if like the difference between doing stuff on a grid or in the continuum or whatever, this should not really matter. And I think I've had all my fun with animated transitions, and there won't be any more in the talk. Okay, so what are the main challenges to mathematicians that we would like to solve? So one thing we would really like to do is, like I said, often we're going to consider our system on like a grid or something like that. And one of the things we would really like to do is be able to take what we call scaling limits. So you imagine making the spacing of the grid smaller and smaller, staying at criticality and trying to say, can you understand what things look like at very large scales? And you know, part of the reason to do this is that the actual like discrete systems are extremely messy. You know, that even though we're working with simplified models, they're very complicated. They're very hard to like do computations with. And the hope is that if you zoom out and take a limit, you know, it's like working with differential equations instead of difference equations or something. It's often much nicer to work like, you know, to do calculus or something instead of doing like finite increment arithmetic. So that's something we would really like to do. And this, by the way, is closely related to the problem of putting quantum field theory on like firm mathematical footing, which is a major problem in mathematical physics. Okay, so that's one thing we would like to do, and I'll say much more about what I mean by that later. Of course, you know, what you would then like to do is hopefully once you've been able to describe what these systems look like at these very large scales, you can actually use that to study the discrete systems that you originally cared about. Okay? And again, the hope is that often these things are sort of intractably complicated, but if you think about them in the right way, once you've zoomed out to very large distances where you want to see this interesting rich behavior, hopefully things become a bit easier to understand. At least that is the case in many examples. Okay? And of course, you know, another major problem is to actually put this phenomenon of universality and so on, like that should be a theorem, right? Ideally, it would be a mathematical theorem rather than just a kind of phenomenon that occurs. And you know, the problem is that these things are generally very hard to work with, and the state of where we are and what we can prove is, in most cases, you know, several steps before getting onto these problems. Okay, so let me give you an example of what I mean by this idea of wanting to take a continuum limit of a discrete system. So this is an example that's very well understood. It's been understood for over 100 years, which is random walk and Brownian motion. So what is a random walk? So it's a random process. So you think you have a particle that lives on a grid, okay? And at every step, you randomly decide to go in one of the directions. So let's say we're in 2D, like in the picture. So at each step, we either go left, right, up, or down, equal probability of each one, independent of everything we've done before. Okay, that's a random walk. And in the early 20th century, it was realized that there is a sensible way of like taking a limit of this process, like as a process. So one thing you might see if you've taken undergrad probability courses is the central limit theorem, right? So one version of that is basically saying if you run a random walk for a long time, if you run it for n steps, it will typically have gone distance about square roots of n. And if you divide by square roots of n and you look at the distribution of that normalized thing, it converges to a Gaussian random variable, i.e. a normal random variable. So you can think that this Brownian motion is like a function version of that. You're not just taking the limit of the random walk at a single time, but the whole process of the random walk, and it's converging to this process called Brownian motion, which, at each time it has a Gaussian distribution of where it is, but it's a process. It's a continuous and nowhere differentiable function, actually. It's a random continuous nowhere differentiable function. It has many super interesting properties that I'm not going to go into. And it was also related to this very important work of Einstein, where he was, giving evidence for like how you could experimentally measure like how big atoms are and things like that. Very important in the history of science, as a turning point where people really started to believe that atoms really existed and that it became like mainstream accepted. Okay, good. All right. So to very briefly summarize like where we are with these problems, and so far I'm keeping things pretty vague, and I'll say some more specific things later. Basically, it remains really hard to understand these things in 3 dimensions, which unfortunately for many of these things is, of course, the most physically relevant case. On the other hand, for quite a long time now, we've had pretty good understanding of critical phenomena in high dimensions. Now, it might sound weird that that is like easier than 3 dimensions, but it is, and I'll hopefully have time to say more about that later. And basically what happens is for many systems, the critical behavior just becomes relatively simple in high dimensions, and once it's at least when you have conjectures about what's going on that are explicit and fairly simple, it's easier to prove them. Right? In 3 dimensions, even having the right conjectures is very complicated. And similarly, well, not similarly, but the other case that's understood quite well now is 2-dimensional systems, where there was a huge amount of progress made about 20 years ago. I mean, and continues to be made now. But in particular, these breakthrough works of Schramm in the early 2000s, and he kind of developed a really nice framework by which you can understand critical phenomena in two-dimensional systems that has really transformed our understanding of these things. You know, this is going to be a pretty broad overview talk. I'm not going to get very deep into any of these things, but I'll hopefully have time to tell you a little bit about it. Okay. So before getting into any of this complicated stuff where it's hard to make any progress, let's discuss this basic idea in another simple case where you can do everything I'm going to explain now. You know, it's going to be a very quick 10-minute version of it, but you know, these things I'm about to explain about branching processes, these certainly could be in the standard undergrad probabilities. Whether they are or not would depend on who's teaching it, whether they want to do it, but it's at that kind of level. Okay. So what we're going to talk about are branching processes. So you can think that a branching process is a simple probabilistic model for how a population grows or how a disease spreads or something like that. So you imagine you start with one particle, and at each step, you have some generation with some number of particles, okay? And each one of them has a random number of offspring, right? So you think that, you know, you immediately die as well at the same time as you produce your offspring, you know, so the generations of this, okay? So this has some probability distribution mu, which is the same for every particle. For example, you could say, you know, I roll a dice and I have that many children. You know, everyone's doing that. Okay. So one thing that's very easy to prove, if you run this branching process and you look at the expected number of particles in generation n, it's exactly equal to the expected number of particles in generation 1 to the power n. This is like a nice, easy exercise in probability. Okay? So in particular, let's define R to be this expected number of children in generation 1. Then well, certainly if R is strictly less than 1, that means the expected number of particles in generation n is actually decaying exponentially as the number of generations increases. Okay? Now, you know, it's a basic fact in probability that if you have a non-negative random variable, then the probability that it's positive is at most its mean, right? This is related to Markov inequality. So in particular, if R is strictly less than 1, then the probability that there are any particles alive in generation n, well, it's at most this expectation, which is decaying exponentially. Okay? So in particular, this process will die out quite quickly, basically, when R is strictly less than 1. Now, what's also true, although it takes a bit more work to prove, although again it's not particularly hard, is that in fact this transition between the process definitely dying versus potentially surviving forever actually occurs exactly when R is equal to 1. So if R is strictly larger than 1, you have a positive probability that things survive forever, and in fact the sizes of the generations will grow exponentially quickly. And the hardest thing to show is that if R is exactly equal to 1, so in this case, in expectation, the number of particles in generation n is just always equal to 1. And in fact, the probability that you survive for n generations is decaying, but it's decaying much more slowly than in the subgroup. Okay. All right, so indeed, the first sentence here is what I just said. So when R is equal to 1, it turns out, so this is exactly the critical case, right? And you know, this is a simple model, but we're already going to see this interesting critical phenomena, fractal geometry kind of stuff appearing even in this very simple model. Okay? So in fact, when R is exactly equal to 1, you do die out almost surely. Like there will be, at large enough generations, there will be no particles alive. But the probability you survive for n generations decays quite slowly. In fact, it decays like 1 over n, right? So this is much slower than exponential. Okay? And in fact, so, you know, I didn't say it, but, you know, as we're generating this process, we can think about making this tree, right? This is a mathematical tree, right? It's a graph with no cycles, right? Where each particle is connected by an edge to its parents and to its children. Okay? And what we can do is, well, we can think about saying, you know, usually this process dies reasonably quickly, but if it does survive for a long time, what does it look like, right? So what you can do, in other words, is you can condition on surviving for n generations, take n to be very large and say, you know, what does this tree look like? And it turns out to be an extremely mathematically interesting thing called the continuum random tree. It's like a random fractal tree, basically. And again, the point is not just that this limit exists, and this is a simulation, not really of the limit, of course, but of just doing this for a large n. By the way, this tree is actually like a two-dimensional fractal object, but you can't really draw it very well in the plane. This drawing in the plane is highly distorted. Okay. And the point is not just that you can take a limit, but it's actually a very tractable object. So this continuum random tree was originally constructed by David Aldous in the early 90s, and it's something you can describe quite explicitly actually in terms of Brownian motion. And so in particular, anything you want to compute about these large random trees that come from branching processes, often if you turn that into a problem about the continuum random tree in the limit, it will be something that has a nice explicit answer. And then maybe you can convert that back to something about the discrete model. Yep. So it's equal. Yeah, this is the critical case. Yeah, if R is less than 1 and you do the same thing, then you'll basically just see a line, actually. The most efficient way to survive for n generations is just to have a sequence of guys that get lucky and you basically just see a line. Whereas something much more interesting is happening R equal 1. Yeah.
When you say the process eventually dies out, is that unless the distribution is always one child?
Yes. Sorry. Yeah, I should have said that. Yeah. Okay. Indeed. If you always have exactly one child, then you don't die out, obviously. So yeah, the theorem that you die out is only if you're not in that one case. Okay, let's do another example, slightly more complicated. This is something that's very famous in combinatorics, which is why I put the discrete math combinatorics courses on the board, which is the Oda-Shreni random graph. Okay, and this is also something that's used a lot in computer science. So what is a random graph? So I guess I didn't actually say what a graph is. A graph is just a collection of nodes or vertices that are connected or not connected by some edges, right? So what is the random graph? You start with n vertices, and then each pair of vertices that could be an edge, you flip a coin to decide whether it's an edge or not, right? So that has some probability p, which is the prime. Okay, and it turns out that the right sort of scaling to see a phase transition here is to take p to be a constant over n. So normally the constant is called lambda. So in other words, that's the scaling that makes the average degree, meaning the number of edges that you have around each vertex, to be equal to lambda. Okay, and this turns out it's actually very closely analogous to this branching process story we were just discussing. So when lambda is strictly less than 1, when you take a very large random graph, it will break up into just tiny little pieces, and there'll be no large connected pieces. Whereas when lambda is strictly larger than 1, you get a giant component which has a positive proportion, a good proportion of all the vertices. Okay, so there's a phase transition from the largest connected component of this graph being very small to being of the same order as the total number of vertices as lambda changes from less than 1 to big. And again, what you see is very interesting, critical behavior occurring in the case where you're exactly on the boundary and you set lambda exactly equal to 1. Okay, so in particular, if you look at the biggest cluster, meaning connected components of this random graph, if lambda is strictly less than 1, it will only be logarithmic in the number of vertices, which is extremely small. When lambda is bigger than 1, you get a giant component. It has a positive proportion. It's the same order as the total number of vertices. And in the critical case, when lambda is equal to 1, the largest cluster has something intermediate. It's the total number of vertices to the power 2/3. And this is all pretty classical now, and you can see the references on the board. Sorry, I think this sentence at the bottom was copied by accident from the previous slide. Ignore that for now. Okay. Although it should be on this slide, really. Okay. So, just as it was possible to understand this fractal geometry and stuff in the case of branching processes, actually something very similar appears in the case of the critical random graph. So if you set lambda equals 1, so the expected degree of a vertex is 1, and you take the graph to be very large, and you look at this largest component, it actually it converges to some limit object, which is very similar actually to this continuum random tree. Right? It's almost the same as the continuum random tree, but you add in a constant of edges to make some sense. So, I'm not going to go into this in too much detail, but again, the point is, this is an object that's very explicit somehow. Of course, in the random graph, the way you generate the object is very explicit, but actually describing what the large clusters are is quite complicated. Whereas here, if I wanted to actually define this for you in detail, I would need you to take some courses first, which should have been listed here, I guess. But, take the probability sequence and make probably some analysis courses, and then you'll be able to understand what the definition of this object is. But it's very easy. It's a much more tractable object than the discrete object that it's approximating. All right. So now it's time to tell you about percolation, which I think was the other title of my talk, the powerful mathematics of percolation. So yeah, thanks for that. I should say though, the trouble is about this stuff is we're honestly a bit limited in what we can prove. So there are powerful problems in percolation. There may be some powerful mathematics, but we'd like it to be more powerful than it is. Okay. So let me tell you what percolation is. So we start with some graph. So in this drawing, it's the square grid, right? And we're going to do actually something very similar to what we did in the random graph, which is just that we flip a coin for every edge, and we choose whether to keep it or to delete. Okay, so in other words, this Erdős-Renyi random graph we discussed before, that's exactly percolation on what's called the complete graph, which is the graph with every possible edge. Okay, so you have this retention probability P, and we call edges that we keep open, edges that we delete closed, and again, we're interested in the clusters, meaning the connected components of this random graph. Okay. Now, the first basic theorem about percolation that makes it interesting is that you do have a phase transition. Let's say we're on grids. Once you get to 2 dimensions or more. So in 1 dimension, if you just have a line, you never have any large components at any value of P. It's not very interesting. But if you're in 2 dimensions or more, then there's a critical probability we call PC, which is strictly between 0 and 1. So that if you're below PC, there are no infinite clusters. And in fact, in a large box, the largest cluster will only be logarithmic in the volume of the box, things like that. Whereas if you're above PC, you have an infinite cluster. It has a positive density in space. So it's quite analogous to this random graph phase transition. Okay. Now, in the particular case of the square grid, it's a theorem of Keston from the early 80s that the critical probability is exactly 1/2. And this is ultimately related to the fact that the square grid is its own planar dual. And this is an important theorem if you want to study percolation on the square grid. On the other hand, you shouldn't get the wrong impression from this, in that it's highly atypical that you can compute PC. So normally, if you want to study critical percolation in other kind of settings, for example, on a 3D grid, you'll have to do it in the absence of actually knowing the value of PC and just use the implicit definition. It's where you transition from having only finite clusters to having infinite clusters. Okay, so this is where my talk maybe gets derailed by this not working. So I want to show you a simulation of the percolation phase transition. Okay. So it has this nice music on. I don't know whether you like it or not. Yeah, I'll play it. Okay, so this is made by this guy Niels Berglund, who's a mathematician, who he has a YouTube channel where he makes loads of nice simulations of statistical mechanics things, and also like wave equation solutions and stuff like that. He has like hundreds of videos on his channel, so if you like this kind of thing, I highly recommend you check it out. And what you should be seeing here, this is what's called site percolation on the triangular grid, which is basically, in site percolation, you're deleting vertices instead of edges. So here, the vertices of the triangular grid are like the hexagons in the hexagonal grid, which is its dual. And what you're seeing is that as time progresses, you're adding more and more random hexagons to this grid. And you see this transition where you go from only having very small connected components of hexagons to having this large one. And I have to remember, so I think the colors are just going to be based on the sizes or something. One thing to note here, I think it's slowing down as it approaches the critical point, so you can see that more clearly. But you should think you're seeing these large clusters emerge kind of very rapidly on a much smaller time scale. And another thing to point out here is that, let's skip ahead to higher resolution one, is that if I were to take this video and kind of pause it when the large clusters begin to appear, which is like here, okay, you get like this very rich structure of what the lattice looks, of what these large clusters look like, right? It's kind of, it's related to that picture I showed you on the second slide, right? That they seem to have some very complicated fractal structure of what these large critical clusters look like. Okay, so let me show you the same, another video that Niels made. This time it's on the 3D grid. So what it's of course harder to make videos that look good about 3D things. So what he's doing here is he's showing you everything that's connected to the left-hand side of the box. Okay, but it's the same thing. You're gradually increasing the density of the number of cubes that you're including, and then you should indeed see that it has this very rapid change. And as it's undergoing that rapid change, you have some very rich structure of what these components look like. So let's see the next one at the higher resolution. So you can see not much is happening for a while, and then, yeah, you rapidly get these large pieces attaching. So, it's hopefully kind of reasonable from this that, maybe there is some way of saying, okay, well, what if the lattice was like infinitely small? Could we describe what it means to do this process? And it's hopefully also plausible to you that that might be quite a difficult question. Okay, so what kind of questions would we like to answer about this model? So one of the most basic qualitative questions is, well, we defined PC as the boundary of these two regimes, right? Below PC, there are no infinite clusters. Above PC, there are infinite clusters. So, what happens at PC itself? You have infinite clusters, okay? And this is a kind of notorious open problem in, let's say, 3, 4, 5, and 6 dimensions. So it's known in 2D, it's done by Kasten. It's known in high dimensions, where it's done by Hara and Slade, but remains a problem we don't have many tools to attack, it would seem, for example, in 3 dimensions. Okay, now, yeah? Yeah, we do know it's computable. It's probably not algebraic. I mean, there's no particular reason for it to be. There are known, like, if you're in very high dimensions, for example, you can write down series expansions for PC. They're actually just asymptotic series, so you can't actually sum them in a divergent series. Like, let's say PC is a function of the dimensions. Okay. Good. So what I want to tell you about, though, is not really about this qualitative question about whether you have infinite clusters of PC or not, but rather it's the question you would like to understand after that, which is, we conjecture that you never have infinite clusters of PC, except in one dimension where PC is 1 and it's quite degenerate. But if you're not in one dimension, if you're in 2 or more dimensions, you should not have infinite clusters of PC, but you should have these very large finite clusters that have a very interesting fractal structure. Okay? And part of the way we would like to understand this is through scaling limits, which I've already talked about. Another way is through what we call critical exponents. So the idea here is basically many interesting quantities should have like power law scaling, like either it's describing something about what clusters look like at criticality, or about how some interesting quantity blows up as you approach the critical point. In fact, I think I explained this much better in a few slides later, so let me skip ahead to that. The way you should think about, the physicsy way of thinking about this, what these critical exponents mean, is basically you have some quantity you're interested in, and you're making observations of the system at some scale, and you expect that this quantity will depend on the scale that you make the observations on according to some power, right? And in fact, if you see things this way, you can think that it's a bit like a dimension of something, right? Like, if you're thinking about lengths versus areas versus volumes, right, they have different ways of scaling in terms of, how the quantity evolves as you change the scale in which you're measuring it. And, it's a similar thing here. You should think of these critical exponents as something like the dimension of something. Also, I should warn you, I have, I think, way too many slides, so you should let me know when I need to get stuff. So one case where you can understand all these critical exponents and stuff very well is in percolation on a tree. Okay, now percolation on a tree is in fact exactly the same thing as a branching process, basically, that we already talked about. Okay, and in that case, again, this is something that's pretty easy to understand. It's well within the range of things you could cover in a normal undergraduate course in probability. And you get all these nice, simple, explicit values. So, for example, let's say C is the cluster at the origin. So, like, the probability at criticality that is larger than n decays like 1 over root. That's one of these examples. And another one would be, if you're slightly above the critical point, you say, what's the probability of the origins in an infinite cluster? It's going to be like order epsilon. So if you're PC plus epsilon, it would be order epsilon. Okay. Now, what are the conjectures regarding d-dimensional space? Well, actually, let's start with the high dimensions at the bottom of the slide because it's easier. So again, I mentioned before that we understand things pretty well in high dimensions, and again, you might find it surprising at first that high dimensions should be easier. But basically what's going on is that as you get to higher dimensions, eventually the model, the critical behavior just becomes much simpler. So I'm talking about this in the context of percolation, but this is true for many other systems in statistical mechanics as well. So basically, once you go to high enough dimensions, the space is like so big that the model, like, it doesn't really feel that it's in a finite dimensional space at all. It just starts to behave more or less in exactly the same way as if there was just no underlying geometry, right? So, one way of thinking about that is that it's the same as on a tree. The other is like it's the same as on the complete graph, basically, like this Oda-Shreni type thing. Again, you can think that's like percolation with no geometry. So, and it turns out that, again, not just for percolation, but for many other models, there's what we call an upper critical dimension, which for percolation is 6. For other, this depends on which model of statistical mechanics you're studying, but there's often an upper critical dimension, above which you have this effect, and you get what's called mean field critical behavior. And again, this kind of means you're not feeling the effect of the geometry. Whereas below the critical dimension, the geometry is having an important effect on the model. And one way you see that is that these critical exponents will change. They'll no longer take the simple values that they have in high dimensions. Okay? And there's basically just one case where we understand this well, which is in 2 dimensions, where you get these funny, explicit rational values of various critical exponents. And this is actually proven, at least in one particular case, slight percolation on the triangulatus, which is what we saw the video of before, where this is actually a theorem that you have all these particular scalings. And this is a long story, but it was conjectured by physicists about a decade or so before it was proven by mathematicians, which is actually a pretty rapid turnaround as far as these things go. There are many special things about 2D that are underlying this. And again, in 3 dimensions, for example, there's no reason to expect that you have such a nice answer. Like probably, we can't even show these exponents are well-defined or anything like that, right? But, they presumably are well-defined, but there's no reason to believe that they're algebraic numbers or anything like that. Yeah.
There are physical significance for these rational exponents?
Yeah, I mean, they come from, depends what you count as physics, right? Often when mathematicians talk about physics, they mean like heuristic math that the details haven't been fleshed out for, right? It's not like, he was asking about the physical significance of these numbers. They are related to things that theoretical physicists are interested in. Whether those things are automatically physical, I can't say. But they have interpretations. They don't come from nowhere. Actually, these numbers are very related to some deep algebraic structure that's hiding in these 2-dimensional critical phenomena that are related to something called the Virasoro algebra. And these are related to the representation theory of the Virasoro algebra. this is a bit beyond my okay. So let's see. I think I'll skip. I had another video to show you. So one interesting case where we have conjectures, in fact we've had conjectures since the 70s, but no theorems yet, is 6 dimensions. So this is exactly at the critical dimension. So it's when you're just starting to feel the effect of the finite dimensional geometry. And again, this is like a general phenomenon that at the critical dimension, you just start to behave differently, and you actually have the same critical exponents, but the scaling differs by some powers of log. Okay? And there are precise conjectures about what these powers of log are. Actually, for all the quantities I wrote down, it's 2/7, but it's not like it's always 2/7. You also get some 1/21 and things like that. And again, this has existed as a conjecture since 1978. But the methods that physicists use to arrive at these answers, like we just don't know how to turn them into rigorous math. There are parts of these methods that we do know how to do that with. It's hard, but we know how to do it with. And for some other models of statistical mechanics, we can now do similar things completely rigorously. For percolation, there's another additional problem besides just the fact that the methods are difficult to do rigorously, which is that there's some conjectural relationship between percolation and some like supersymmetric field theories or something, and like nobody has figured out how to do that properly. Okay, so what about 3, 4, and 5 dimensions? So even for physicists, this is still considered hard, and there probably just isn't really a nice answer in some sense. So one very popular approach, until quite recently it was really like the only approach, is something actually it's normally called the epsilon expansion. I kind of think every expansion is an epsilon expansion, so I prefer a more specific name, but if you want to talk to a physicist about this, you should probably call it an epsilon expansion. So I'll call it the Wilson-Fisher expansion. So Wilson and Fisher, so I should say Ken Wilson is sort of a very important figure in the development of this theory on the physics side in the 70s and 80s. He won a Nobel Prize for this work. He was also a grad student at Caltech. I have a picture of him on a later slide. Not sure I'll get to that. So he had this idea, okay, he was studying a different model, the Ising model, which is a model of paramagnetism. And in that case, the critical dimension is 4. And he's like, okay, thanks to partly his own work, 4 dimensions and higher was solidly understood by physicists at that point. 3 dimensions remained very hard. So he said, well, let's not try and do 3 dimensions directly. Let's imagine we have a magnet which is 3.999 dimensional, right? And like, can we understand how the exponents and stuff are just changing as I slightly move away from the relatively easy case of the critical dimension? Okay. And so what they can do, and again, this is something that is very hard to make into rigorous math as things stand, is to give these asymptotic expansions. So, for example, for percolation, these are 2 exponents. One of them is describing the decay of the point-to-point connection probabilities, another describing the Taylor volume. And these have some conjectural expansion. So, one thing to note about this is the coefficients here get extremely complicated, and it's very, very hard to compute them. And people still write papers in physics like computing the 5th coefficient in the sequence or something, right? Like there are really people writing papers on that, and these papers have like formulas that take up a whole page and things like that. So they're very complicated. Yep. Yeah, well, okay, part of it is that they don't really work with percolation, so this is what I was saying. So they have this vague idea that it should be equivalent to a certain spin, like field theory, the phi 3, phi cube field theory, but with a 0 component spin, like a field taking values in R to the 0. Of course, that's like nonsense. There are ways of making sense of those 0-dimensional fields using supersymmetry, but nobody has successfully come up with a rigorous version of this equivalence of percolation. So actually these kind of things have been done successfully for some other models where we know how to do that first step. In that case, it's merely difficult, but here there's a starting point that we don't really have. You know. Yeah, it's partly like it's just something. There's a first key step that's just very vague what it really means. Yeah. But aside from that, there's just the case that even when you don't have the problem, it's technically very hard. And the issue is basically like as mathematicians, we have to prove that every negligible term is actually negligible. And this is extremely difficult, actually. Okay. Another thing is like these expansions are supposed to be divergent, so again, you can't even really sum them. There are issues with this, but it has been partially made progress in some. Okay, and now I have to decide what I'll actually do in my last 5 minutes. Okay, maybe I'll say this. So, one thing I mentioned before is you should think that critical exponents can often be thought of in terms of fractal dimension. I think it's a nice thing in the context of this kind of talk to tell you a little bit about fractal dimension. So I was sort of saying about this before, right? One way you can think about like the dimension of lines and squares and cubes and so on is about like if you scale, like how many copies of the object exist, you know, in the rescaled copy, right? So if you take a line and you scale it by a factor of 2, it's like you took 2 lines and put them next to each other. You take a square and you scale it by a factor of 2, it's like you put 4. You take a cube, it's like 8 and so on, right? These are 2 to the 1, 2 to the 2, 2 to the cube, and 1, 2, 3 are exactly the dimensions of these different objects, right? Whereas, like, if you take this thing on the right, a fractal called the Sierpinski gas cube, right? You can see if you scale up by a factor of 2, you get like 3 copies of the thing, right? So in this case, well, you have to think of 3 as being a power of 2, right? So the dimension is log base 2 of 3, which is like about 1.5. And there are some other nice examples numerically. Get the dimension of the coast of Great Britain is about 1.23 and Japan is about 1.14. Anyway. Okay. So often you can think about these critical exponents that I was discussing in terms of some fractal dimensions of this picture that you see, right? So, you know, you could look at the dimension of the clusters themselves. You could look at the dimensions of the boundaries. You could look at some other features, like maybe about how 2 clusters like touch each other or something. And basically, in high dimensions, again, we understand things pretty well. And in fact, this is something I'm working on right now. Hopefully, the paper will be out pretty soon. We can actually prove that these large clusters converge to exactly the same thing, the continuum random tree, that you got in the models with no geometry, the branching processes, the Schwenning processes. In particular, a consequence of this is actually that the dimension of these large clusters is 4. We don't have time to explain that, but that's one of the things you get. Now, the convergence to the same scaling. Okay. What about in 2 dimensions? So I mentioned that, you know, our understanding of this like progressed a lot about 20 years ago, although it still continues to progress now. And basically, Oda Tram discovered this way of describing what these scaling limits should be. It took a few years after that in collaboration with other people to prove that they actually are those things, which are called the Schramm-Loeffler evolution curves. And again, this is a more complicated object than Brownian motion, but part of the point, and there's different ones that give scaling limits of different 2-dimensional systems. But part of the point of this is that, again, it's actually a highly tractable object you can do computations with. Okay? And it was finally proven by Sasmonov, who's another Caltech alumni who won the Fields Medal in part for this work in 2010, that actually this 2D percolation actually does converge to this scaling, this Schramm-Loeffler evolution. Okay, so one consequence of this, and of course I'm going to use the extremely rapid version of this, is that in 2D, the fractal dimension of these percolation clusters is 91/48, which I just find to be such a bizarre number. Actually, if you think about like most fractals, like natural fractals, like these Sierpinski type things, they don't have rational values to dimension at all. Like it's usually the log of something. So it's a bit strange in some sense to have rational values particle dimension at all that are not integers. Okay. So, okay, I should probably be wrapping up soon, but you know, I talked a bit about, you ask what physicists know and we don't. So most of these things that are done, they're using this framework of what's called the renormalization group that was developed by another Caltech alum, Ken Wilson, who won the Nobel Prize for his work on this. And he kind of came up with this very systematic way, like method of studying these kind of problems. One of the issues with this in math, it's very vague actually. Like it's not really like, it has this, it's often called renormalization group, but the group has nothing to do with the mathematical meaning of the word group. And it's not really a single method, it's like a large family of slightly different methods, and there's a lot of art in how you do it exactly. So one thing about it's just very technical to do. I think even Ken Wilson himself, he described it as like a method of last resort. It usually will work on any given problem, but even if you're not proving everything, it's comparably difficult compared with if you have an alternative. So this is difficult to make precise even in the best of circumstances. And for percolation, it just there wasn't really a way of doing it for percolation. People kind of supposed that there were some other systems that should be the same, but they didn't really prove that. It wasn't really justified. They didn't even really describe what these other systems are even. So there are a lot of problems with that. And just to end on a little bit about, what I'm actually doing. So I think, for the current and future generations of mathematicians, like working in this kind of area in mathematical physics, I really think it's time to make some real progress on 3 dimensions, right? Which is hard. So, and it's a hard thing to just dive into because there's just sort of absence of tools. So, one thing that I've been doing a lot recently is working on these slightly different models, which are called long-range models, which they exhibit a lot of the same kind of phenomena as the nearest neighbor models, but for these I've actually been able to prove quite a lot. So, it's the kind of problem where maybe attacking it head on is maybe not so wise. I mean, everyone should try doing that. You should always try being arrogant. Just do the thing, try to do the things people tell you can't do. But if that doesn't work, you might try and find a easier problem, which is capturing some but not all of the same difficulties. And I'd say that that's kind of the case for these long-range models. They have some of the difficulties of the 3 dimensions, but not all of them. And for this, we can actually prove quite a lot. And part of what this has meant is developing some version of this Wilson-style renormalization group method, but which is applicable to percolation without going through some whatever supersymmetric field theory or whatever that we don't really know exists. So I think I'll finish things there, and thanks again for your attention.
In the previous slide, you said it's hard to make work. So why is it limited by it says 3D?
Well, basically what people do in 3D is they do this epsilon expansion stuff. And, in fact, if you write down these expansions, again, you can't really write them down to infinite order because they're extremely complicated. And even if you could, there'd be divergence, so you'd have to think about complex dimension and Borel summation or something. But you write down a few terms and then you plug in epsilon equals 3 or something, and it actually gives you reasonably good answers. But,
You said it was for a problem where water freezes and temperature.
oh, well, yeah, okay, so actually water particularly I think is super complicated because there are like 12 different phases of ice and all this stuff. But even just more broadly, if you have other models of like, it's very hard to prove anything about solidification phase transition. So you imagine you have like some model of particles that are in space, and you want to say once the density gets high enough, they're like forced into some kind of crystal structure. So actually, this is something was, I think, first proposed by Kepler, actually, kind of amazingly, that this was the mechanism. But like, the reason why you get solids forming is that once things are dense enough, they're like forced into a regular structure, right? You can see it if you put like a lot of balls in a jug or something, right? Once they're dense enough, they get forced into like a lattice structure. And yeah, the trouble is you want to actually prove that. So even proving the kind of infinite density version, like that if the balls are as well packed as they possibly can be, that they have to take a lattice structure, right? This was like this Hales's theorem that was very difficult in the 90s in 3 dimensions, in like 8 and 24 dimensions. It was done by Vyazovska, who won the Fields Medal for that fairly recently. And if you want to prove these things about crystallization, you need to show not only that if things are as well packed as possible, they have to be a crystal, but you have to show if they're just if they have density nearly as large as possible, then most of the configuration space of doing that is on things that look like a lattice, that are some small perturbation of the lattice. So it's like you need some much, much, much stronger version of these kind of things about optimal packing or something like that. I mean, it seems actually very, very hard. No, I think they're really just about. I mean, I don't know too much about this, to be honest.
Also, when the superbrownian motion comes in, like supercritical
No, that super Brownian motion is that's getting into critical population.
Okay.
The word super,
Yeah, what's the super?
I don't really know what it refers to exactly. I mean, I know what the object is. I don't know why it's called that. It's not. It's certainly not the same super. It's super.
All right. Thanks everybody for coming. Maybe another round of applause. And yeah, if you enjoyed the talk, tell your friends. Hopefully we can get more people coming for the next one, which will be Professor Elena Montalvan. Topic to be announced sometime in the next few weeks. So yes, keep apprised. There'll be emails. Yeah. Okay. Thank you all for coming.